Well, I guess the impact of MRI has been huge around the world. I mean, it's a premier diagnostic imaging technique.
It's so incredibly versatile. You can use the different parameters with MRI to get lots and lots of different filters on your images, and every single one of those will give you different information.
The thing that I really love about MRI is it's so variable. Ultimately, all of science is down to kind of careful hard work, whether it's looking at pictures or looking for patterns in data. So we discovered a new physiological phenomenon just from looking at MRI scans. I can do all this clever physics. In the end, just looking and making observations makes a difference.
And I came to Nottingham and Peter showed me his lab. They were coming to the end of an era of working in solids, and he was looking for something new to do. And he thought that he could make an NMR version of X-ray diffraction. And he knew that he could do that using magnetic field gradients, the essential ingredient for MRI, but he didn't have strong enough field gradients to separate the atomic layers, so he built models. He had little layers of camphor, 3 or 5 layers of camphor, and he demonstrated that through the use of gradients he could separate those planes. But pretty soon he realised that biological samples were much easier. At the time, the instruments were designed to put test tubes. And the first human experiment was actually that of his then PhD student Andrew Maudsley. He could just put his finger into the magnet and an image was recorded of that. And that was shown to the Medical Research Council and was sufficient for them to invest in the new technology.
Dr. Mansfield managed to take a picture across the inside of a finger. Now he's constructed this monster magnet, big enough for him to build up pictures anywhere inside the human body. The guinea pig for the first test was Dr. Mansfield himself.
Fine, okay then, press the switch and let's go. Okay.
This is the very first picture of a human body taken this way anywhere in the world. The brown shape at the top right-hand corner is his liver, down at the bottom is the spinal cord. Now, doctors will have to learn to look at the body in a completely new way. Unlike X-rays, both the bone and the soft tissues can be seen clearly. And, as far as is known, unlike X-rays, this method causes no harm to the body.
Ever since I came to Nottingham, really, I've focused on using MRI to make measurements about the human body. We were looking at very high-speed imaging. That's what Peter Mansfield was doing. So imaging, he used to say, in a snapshot. And that allowed us to effectively freeze the movement of the fetus. And that's kind of where the whole programme started from my point of view. So the other example of this was looking at the marker for what has become sort of an MRI marker for Parkinson's disease. So we were looking at high-field scans from the 70s when it was new of patients' brains when they had Parkinson's disease and patients who didn't. And we were expecting there to be changes in the part of their brainstem. And so we just lined up the images, and printed them out in a sort of grid. One side had the Parkinson's disease, one had the healthy controls. And it was barn door obvious at 70, the difference. And that has now become a marker that's been investigated quite a lot by a lot of other people in the world to try and work out when in the disease it becomes apparent.
So at the moment I'm working on a Medical Research Council funded programme grant, and we're trying to disentangle the relative contributions of normal ageing from hearing loss to do with noise exposure, and from noise exposure that hasn't yet caused hearing loss. It's incredibly exciting. I mean, I spend all day, every day looking at brains, so I guess I forget how exciting it is sometimes. It's a trivial matter to image the brain doing its normal jobs. Within 4 or 5 minutes on the scanner, I can get a map of a person's brain, which parts of the brain are responding when they're listening to a sound, compared to which parts of the brain are doing other things and are not responding more when they're listening to a sound.
Unlike MRI scanners, which typically take images of brain structure. We want to go further than that. We want to be able to make images of brain activity. So when we're interested in brain function, obviously we need ways to make the brain function. And if you're lying inside an MRI scanner, it's very difficult to evoke naturalistic behaviour. So where the OPM MEG system perhaps differs is that actually you can just wear it like a helmet and behave naturally. A child could wear it and play with a toy, or maybe an elderly adult could wear it and try to go for a walk. So I think that's what one of the things that's quite exciting about it is the fact that we can do this naturalistic behaviour whilst measuring brain function.
MRI has this habit of reinventing itself every 5 or 10 years with yet something else that it can do that nobody had thought about. No, I think that's a certainty, but what it is, we'll have to wait and see. But there'll be a lot of fun.
I think the new facility that we'll have here will be part of, I guess, the further development of MRI. So higher field offers lots of exciting opportunities. Take one example, it should allow us, when we can use MRI to look at brain function. We can start to probe brain function at the spatial level where the brain's organisation is really important. So looking at structures which are hard to discern with the currently available technology. We named the centre after Sir Peter, who became Sir Peter Mansfield Imaging Centre relatively recently, and so it's really fitting that this new facility, which is going to be important for nationally and internationally, carries his name, and I think he'd be hopefully very happy to be associated with it.